computer. We'll let the next speaker introduce himself and the topic, and he'll be giving the next two presentations.
All right. Hey, folks. So this is now the Climate Science Mini Symposium, I suppose. So just out of curiosity, as a show of hands, how many of you folks are familiar with geospatial stuff or do geospatial processing? OK, sweet. So a couple of people. OK, so I'll sort of start from the basics here. This is mainly these next two presentations are mainly going to be using the Julia Geo ecosystem. Well, I guess I should introduce myself first. So I'm Anshul. I work at Julia Hub now, but I do a bunch of geospatial processing stuff as well. I'm the author of GeometryOps.jl. I do a bunch of stuff with the Marquee plotting library. And yeah, so today I really mostly just wanted to give an update on this GeometryOps library, which is a sort of initially intended to be a grab bag of random geometry processing utilities, right? So geometry being, maybe you have a couple of points on the Earth, you have some lines, you have some polygons, things like that. So I'm not going into the full 3D, CAD meshing kind of thing, right? That other people have done that in Julia to quite some success. And so this is mainly 2.5 dimensional stuff. And so the reason that I'm emphasizing the sphere here is because we do happen to live on an approximately spherical object. And many people have tried to make that spherical object a planar object, and that always comes with some trade-offs. But you can also perform computations on the sphere itself, right? You can just use three-dimensional coordinates on a unit sphere, and that gives you a lot more accuracy for some things, right? In some crazy edge cases, you may even want to compute directly on the ellipsoid that is the Earth, or the ellipsoid that is something else. So you may want to find the area of a crater on an asteroid, for example, which is some crazy oblate ellipsoid or something. So there's lots of stuff that comes with, there's lots of nonlinearities and fun stuff that comes with spherical processing. So what is GeometryOps? What is this thing, first of all, right? It's a grab bag of geometry processing tools. So GeoInterface.jl is sort of the central package. It's an interface for geometry that defines how you can access a geometry and defines how you can convert one form of geometry to another, right? And so the idea is you can say, most ecosystems have a single geometry representation, right? You read something from a file, you read it from a JSON or from a binary or from shapefile or something, if you guys are familiar with that. And those all save in different formats, right? And with different memory layouts. But at the end of the day, in most ecosystems, R, C++, Python, right? You convert into one representation. Of course, this being Julia, we weren't happy with that. And so what GeoInterface allows you to do is to use any in-memory representation of geometry. And you can do all sorts of crazy tricks, right? Like you can interleave your points. You can have like 3 different vectors. You can do all sorts of crap. But the idea is that you just have one consistent interface to access those. And you can convert from one form to another. So this is really useful for if you want to write a file, for example, right? You can just, all the writers just work on any GeoInterface geometry. And so we're able to call out to all of these random C libraries that have had decades and decades and decades of work. But then if you want a different algorithm, you can also just write it in Julia or call out to a pre-existing Julia implementation. So yeah, GeometryOps was meant to be the grab bag for those sorts of algorithms. Any GeoInterface compatible input works. So that's stuff read from files, stuff that you created in memory, stuff that you got from a database. Some of its capabilities are you can do geometry clipping and intersection, right? So what's the intersection of these two polygons? Do they intersect in the first place? Do they only touch each other at one point? Do they touch each other on a line? Right, things like that. You can do interpolation within a geometry, or so if the border of your polygon has some value associated with it, right? And that's actually a flawed version of that interpolation algorithm is how I got this logo. So I think I had an off by 1 error in the indexing, so it ended up doing that. But you can manipulate coordinate systems, so you can go from one coordinate reference system to another. But the really cool thing that a lot of this is built on is this framework to automatically decompose geometry, right? So going all the way from a table with associated attributes, right? So you could have like countries, which could be polygons, could be multi-polygons, right? So a single polygon is just an exterior and a bunch of holes, but it has to be contiguous. A multi-polygon can have, for example, Well, Pennsylvania doesn't have any islands, so that's probably a bad metaphor. But it could have, for example, a country and some islands associated with it, right? And those islands do not touch the country at all. They're completely separate. So this gets really painful because all of these structures are different things, right? Like you could even have completely different things. You could have a data frame with polygons, with multi-polygons, with lines, with multi-lines, right, with points. And so let's say you wanted to project those from latitude, longitude to a different map projection, right, for example. If you tried to do that yourself, well, you would have to see, okay, is this a multi-polygon? If so, then decompose to polygons and call the polygon routine. Okay, is this a line? Okay, decompose to points and call the point routine, right? And so what this apply and apply reduced framework does is it lets you specify a target geometry type that you want to accept, and then anything you pass in, if you pass in a vector, that each element of that gets decomposed, and whatever the result is from apply gets reconstructed and put back into a new vector, right? If you pass in a table, you maintain all the attributes and things like that. So this is a really a pretty cool framework. And if there's interest or time, which I'm already running short on, I can show some code examples. But some of the new stuff that we've got is tree optimizations in GeometryOps. So you can accelerate a lot of your intersection computations by basically grouping geometries into sort of areas, right, and building up trees on that. And so generally people call these spatial trees, R trees. If you're familiar with databases, you might have heard of R trees or B trees, right? But the cool thing about having this in Julia is I can experiment with any implementation. And so I can also not necessarily have trees with rectangular bounding boxes. So someone in the Max Planck Institute in Jena is using this interface that we've developed to use trees with basically caps on a sphere, right? So you have a point and some spherical angle around that, and that defines a region on a sphere. And so that becomes your bounding box of your geometry. So I don't know if this video will show particularly well, but this is building up a classical R tree on a circle, right? And so you'll notice that it's pretty deep because the node capacity was only 10, but each of these, this is where it gets iffy to show. But each of these boxes, so the green boxes are a lower level, the orange boxes are a higher level, the blue boxes will be the highest level. And so you can see that this sort of builds this up in this arbitrary order, right? But there's this other algorithm which someone had implemented in a C library called natural indexing, where you basically say, okay, let's say I have a polygon, right? If I go from vertex I to vertex I plus 1, those will generally be sort of correlated, like they'll kind of be pretty close to each other. And so I don't actually have to waste time sorting all my points and binning them into an R tree. I can just walk along this polygon, and every end points, I create a new box. And so this is a natural tree on a circle. You can see that it's got a lot less layers, but it's got about the same amount of spatial fidelity. But the cool thing is if you do that on a complex geometry, so this is the state of Texas. This had about 7,000 points, I think, from memory. I kind of simplified it a bit. And so you can see that, okay, over here, this is one of the disadvantages of this tree, because this is basically 1 point, 1 point, and then 1 point, right? And so that whole spatial area kind of gets eaten up into one node. But if I go and look at the STR tree, there we go. If I go and look at the STR tree implementation, what happens is that so each of these has certain advantages and certain disadvantages, right? And if I forward this a bit, you will see that this tends to build up these very, very large nodes that have a very, very large Y span because it's sorting in X. And so this is actually a much less optimal tree to query on than the previous one for some cases. And so you can keep doing this crap. There's also a new interface for these things called Manifolds. So this is kind of where the spherical stuff comes in. So most geometry processing algorithms will be kind of similar, will have kind of similar implementations and kind of similar ideas behind them, no matter if you're doing it on a plane, a sphere, or an ellipsoid, right? So let's suppose you wanted to calculate the area of a polygon or the length of a line. Well, I mean, conceptually, that's simple enough. It has the same input. You have the same parameters if there are any. But what space are you computing this on? So the default thing that everyone does is just, you assume it's on a plane, right? If you try to compute the area of the US based on a regular just shoelace area formula, you will get a completely nonsensical answer because you're just computing it in latitude and longitude. If you try and project to some optimal coordinate space, okay, you'll still have spherical warping, you'll still have this, you'll still have that, right? But with this stuff, you can specify, okay, I want to compute this on a plane. No, I want to compute this on a sphere. No, I want you to compute this on this particular ellipsoid, right? And so geometry operations can just look at the manifold that you have defined and dispatch on that. So there's a new, to build on top of that manifold thing, there's a new algorithm interface as well, right? So you can store the manifold and several parameters in this algorithm by which you compute or by which you perform some operation. And where this really gets interesting is with polygon intersections and tree acceleration for those. Because you can say, okay, I know that my polygons are pretty weird, so I want to go with the safe option. I want to have an STR tree, and I want to bin all the lines into this tree structure and make it really fast to find which lines intersect which other lines, right? Or for example, there are multiple ways to calculate the area of a polygon on a sphere, right? And so which one do you want to choose? Well, you can just choose any of them. The developer doesn't have to make that decision. You as the user have the freedom to do that. So yeah, I think I'm probably a bit over time on this. But yeah, any questions so far? No.
Hi, very cool. You mentioned that you can that it works on data sets that come from any source that you have in memory. So if you have like a large mess, millions of cells that was exported in like an NK gold file,
I don't think,
would you be able to import that?
I don't think I have ever encountered those. So we probably didn't write a library to import them. But if you can import them into Julia, then yeah, absolutely. You can just represent them.
I've been able to import them into VTK-based library in PyVista in particular with Python. Maybe a solution if PyVista is able to export it to something you can use.
Sure.
You may just do the PyCall method and wrap it that way.
That would be very possible. Yeah.
Okay.
And the cool thing with GeoInterface is you could actually define the GeoInterface methods on your Python object.
Okay.
So you could just directly use that and access those, right? Or you pull it to Julia or something, but yeah.
Okay.
That's also an option. Cool. All right, let me see here. I may have to do this. Oops. Sorry, just have to log into this other thing because I made this in PowerPoint. All right, so let's see here, slideshow from the beginning.